All right, moving right along. So we're going into Gay-Lussac Law for gases, okay? This dude deals with how pressure and temperature affect each other, okay? And we keep the amount and the volume the same. So we're just looking at pressure and temperature for Gay-Lussac Law. Okay, Gay-Lussac Law. So again, we're dealing with how pressure and temp affect each other. Okay, so those are my two variables I'm dealing with. I'm going to keep the amount and my volume constant. Okay, all right. And these dudes are also directly proportional. So as one goes up, so as one guy goes up, the other guy also goes up. Okay, so we're going to graph it. Temperature would be my x-axis. Okay, so temperature would be on my x-axis. Pressure would be my y-axis, okay? And as one of them goes up, if temperature goes up, the pressure would also go up. So it'd be a graph that looks like that. Easy money. All right. Real examples of Gay-Lussac's law would be like if you've ever played basketball and you've played basketball on a cold day, or you go out to try and play basketball on a really cold day, your basketball feels flat. Right? You're trying to bounce the basketball, but it feels flat. That's because the temperature is so low that the pressure inside your basketball is actually also lower. So it's not bouncing as much. Other real world examples. Aerosol cans or like hairspray cans have a temperature warning, like do not exceed this temperature. And the reason they have that is because if the temperature rises too much, the pressure is also rising inside that can, and it can rise so much that you could literally have the can explode. Okay, so that would be bad. You don't want a bomb to accidentally go off in your bathroom or something. Okay, so that's why they have those temperature warnings. And another really good example of this is like how a bullet would fire out of a gun. So when the gunpowder actually ignites, you're making very hot gas. Okay, so that gas is super hot. The heat inside the gun, the heat inside the barrel, right? It heats up so much that it's building up the pressure. The pressure builds up so much that it will literally shoot the bullet out of the gun. It's just gas laws, okay? All right, so there's Gay-Lussac's law. These dudes are directly proportional. So I get my initial pressure divided by my initial temperature equals my final pressure divided by my final temp, okay? So this is my initial conditions. These are my final. Okay, pressure should be in atmospheres. Temperature should be in Kelvin. You have to be in Kelvin. Do not leave something in Celsius. Please. Okay, it's the number one just looked over thing on a quiz or a test. You just accidentally left it in Celsius. Don't let it be you, all right? Okay, one example, because that's all you need, all right? So if we had a 0.5 liter aerosol can, okay, so that's like hairspray. And it's compressed, right? It's compressed gas. So the internal pressure has a pressure of 10.3 atmospheres. That would be a lot higher than room pressure. Room pressure around us, we're almost at sea level, so we have about a 1 atmosphere, 1. So this would be 10 times the amount of air pressure that we feel inside that can, okay? So room temp, which is 25 degrees Celsius, okay? And it also says do not exceed a temperature of 45 degrees Celsius, okay? Why? What's the pressure if you got to 45 degrees Celsius, okay? And if you notice, right, we're dealing with Gay-Lussac Law, which is only dealing with pressure and temperature, but there was volume given to you. This will happen a lot in any type of gas law question or just any type of question at all. They will give you extra info to try and screw you up. Who cares how big the aerosol can is? Nobody. Okay, all we care about is the pressure and the temperature for Gay-Lussac Law. All right? So ignore the extra information that they're giving you that'll try to throw you off. Okay? Now, also remember, you don't want to be in Celsius, you have to be in Kelvin. So first things first, 25 degrees Celsius plus 273 is 298 Kelvin. 45 degrees Celsius plus 273 is 338. No, not 348, 318. Okay, I can do math. Not in my head though. All right, so I solved for this in Kelvin. Now I can actually plug in. And I probably that we haven't used on this page. Why not? So I would have, here we go, pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. And I just plug stuff in, okay? So my initial pressure, 10.3 atmospheres, divided by my initial temp, which would be 298 Kelvin, which would equal my final pressure. I don't know what that is. I'm trying to find out. Divided by my final temp, 318 Kelvin. Okay. Do your butterfly method, or again, whatever method works for you. Try and scoot this up so you can see it. So I would get 10.3 atmospheres times 318 Kelvin equals pressure 2 times 298 Kelvin divided by 298 on both sides. Okay, that cancels. Kelvin and Kelvin cancels. I'm gonna scoot this up. All right, and I get an answer. Multiply those guys together, divide. Pressure 2 is equal to 10.99 atmospheres. Okay, so my pressure has gone up. So potentially, like, maybe they have that warning on the can because if you reach 11 atmospheres, it'll explode or something, right? So we don't want to have the pressure build up too much in that aerosol can. All right, and of course, draw your initial and final conditions. So your volume doesn't change, right? Gay-Lussac Law is only dealing with pressure and temp. So make sure that you draw your initial and final volumes relatively the same, right? I'm not going to, again, who's going to take a ruler and measure it? I care that you understand the concept, right? But initially, I also didn't change the amount. So if I started with 3 particles, I ended with 3 particles, okay? Just to show that you understand the concept. I did change the temp, right? The temperature went up. So my arrow starts smaller and my temperature gets larger. My arrows get larger to show that the temperature increased, which would mean the pressure inside this box is also increased. All right, that's it. Gay-Lussac Law, okay? Pressure and temp, how those two things interact. And we're done.